All right. So good afternoon, everyone. So this is a submission for assignment 3, and then this is return of your midterm and any assignments that haven't been picked up. These ones are in alphabetical order, so they're easy to find. Okay. My solutions to the midterm have been posted on the course website. So if you want to kind of take a look at what you did and how it was graded and compare it to what my solutions look like, then by all means, feel free to do that. The average was about 62, I think, in the end, somewhere around there. Hopefully, what I was trying to do with the midterm is I was trying to make it so that the calculations were not long and difficult. So, for example, the only integrals that you had to do were integrals of like polynomials and like trig functions like sine or cos. So I was trying to make it so that you had to do the kind of, I don't know, the mechanics of a quantum mechanics type problem. You had to go through those procedures, but the actual calculations were meant to be relatively straightforward. So that's what I was going for. Whether or not I achieved that, I suppose, is open to interpretation. Okay, so the things that we were talking about were this eigenvector equation where we imagine some operator acting on some quantum state, psi. If it returns a number multiplied by that same state again, that's our eigenvalue equation, where psi would be called an eigenvector of operator q hat, and it has eigenvalue q. What we worked out last time, I guess it was a little while ago, was that if you had a Hermitian operator, then its eigenvalues are going to be real. We proved that. And we also proved that two eigenfunctions with distinct eigenvalues would have to be orthogonal. And so one other result that I'm just going to throw up there because we're going to use it today was that we looked at the eigenfunctions of the momentum operator, and they ended up looking like this. It was this exponential e to the I px over h bar. So we're going to make use of that in one of our examples today. So where we are is we're kind of in the middle of chapter 3, and we're going to do 3.4, a generalized statistical interpretation. And so here's where I want to start. If some observable q, so these q's can be functions of maybe position and momentum. If that is measured on a particle in state psi of xt, the result is certain to be one of the eigenvalues of the Hermitian operator q hat. And so that's going to be some function of the x, the position operator x, and the momentum operator minus I h bar d by dx. Okay, so for a discrete system, so this is a system where there are a set of eigenfunctions that are separate and can be written down, and then we can expand any other vector in terms of some superposition of these states. We also had continuous states, and for that, we had like the position eigenfunctions and the momentum eigenfunctions are examples of continuous systems. But so let's start with a discrete system. The probability of getting, we know we're going to get an eigenvalue, the probability of getting a particular one. So let's say eigenvalue Qn associated, associated with eigenfunction Fn is the C coefficient squared, where we calculate Cn using these inner products. So if we have a state psi, it could be written as a superposition of the eigenfunctions Fn and the coefficients in front of the expansion of psi is going to, if you square those coefficients, the absolute square, you get the probability that a measurement will return the eigenvalue of this eigenfunction. Okay, now for a continuous spectrum with real eigenvalues, Qz, same language associated with eigenfunction Fz. So Z might be like, if we're talking about the momentum eigenfunctions, this would be Fp of x, which we wrote up at the top of the slide. So we'll use that later today. So Z is representing the coordinate system that we're thinking of. Either momentum space or position space are common examples. The probability of getting a result between Q and dq is, well, it's going to be the Cz coefficient squared, but this time we have to multiply by the width of the interval. So we're going to get a momentum between some value P and P plus dP, something like that, where the Cz is again given by the same kind of inner product. Okay, so what I want to do is I just want to check some of these properties. If the probabilities are given by Cn squared, we should be able to confirm that if we sum all the Cn's, they should add up to 1. So let's check that the sum of all of the Cn squareds equals 1. So to do this, what we're going to do is we're going to expand psi x of t in terms of the eigenfunctions Fn of x. Okay, so that might look like psi is going to be the sum over all n, and then we have the Cn coefficients multiplied by these eigenfunctions. So this Fn are the eigenfunctions. Okay, so what we could do is we could take the inner product between our states. If the state is normalized, that inner product has to be equal to 1. And well, let's see, it's just going to be this sum times that sum again, but we have to take the complex conjugate. So it would look like the sum of n prime Cn star or Cn prime star. And then we have our state, our wave function. So that's going to be, sorry, I want to do something like this. Let's do something like this. Let's get the notation to be consistent. Okay, so I have to take the conjugate of this. So I got to flip this thing around. And so we'll have a fn prime. And then we have to multiply by the sum of n, cn, fn. Whoops. All right, so what I'm going to do is I'm just going to rearrange these things a little bit. So I'm going to take this inside the second sum. I can do that because this is an n prime. So as long as I don't have any n dependence, I can move this inside the sum. So we're going to end up with n prime, cn prime star, sum of n, cn, fn prime, fn. Okay, but what we proved last time is that these two eigenstates are going to be orthogonal. So this is going to be 1 if n prime and n are equal, otherwise it's going to be 0. So then we have n prime, cn prime, the sum of n, cn, delta n, n prime. But this sum is going to be like C1 times 0 plus C2 times 0 plus C3 times 0 and so on until we get to Cn prime. Then it's going to be times 1. So only the Cn prime will survive. So this will be Cn prime. Now I forgot my conjugate somewhere. So that must be right here. Complex conjugate. All right. And so therefore, this is equal to sum over n prime, cn prime star times cn prime. Okay, but now that I have just a sum over a single variable, whether I have the prime there or not doesn't matter. So I could drop the prime cn squared, and all of that has to be equal to 1. So this 1 must be equal to this last result. And so therefore, as we wanted, these probabilities, these Cn squared probabilities are going to sum to 1. Okay, so that's good. So our probability sums to 1. All right. What about the expectation value of some measurable quantity? Maybe we want to measure the momentum. And so what we would do is we would find the expectation value of Q. So we have all these replica systems. They're all set up in exactly the same way. And then one by one, we measure the momentum on all of them. We build up this distribution of measurements, and we want to know what is the average value. That's the expectation value. And the way, as you know, that we calculate these expectation values is we operate on our state with Q hat, with the operator, and then form the inner product with that state. Okay, so this is going to be sum over n prime. It's going to be very similar to what we just calculated. The only difference is that the operator acting on psi is going to return a eigenvalue and the state back again. Let's see. Actually, I got to be careful here. Let me do this properly. So then we'd have the sum over n. Here, let me do this slowly. Fn prime of x. How did we do it? Fn prime. Oh God, sorry, keep making mistakes. So Fn prime. All right, and then we're gonna have the sum over n, q hat acting on Fn, and I just need my Cn coefficients in there. Okay, so this is better. This is what I wanted. So now this is q hat acting on eigenstates. And so from our eigenvalue equation, it's going to return Qn and the eigenstate back again, like so. Okay, and so now we can do the reordering like we did before. So let's see, sum of n prime, Cn prime star. And then I'm going to put the sum over n. And then we'll have our Cn. We'll have our Qn factor. And I'm going to take this Fn prime inside the second sum. And it's going to be the inner product with Fn. This is the same delta function that we had before. If we evaluate the sum over n, we're going to get an n prime here and here. So this is going to be the sum over n prime, Cn prime star, Cn prime, Qn prime, which is the sum over n prime, Cn prime squared, Qn prime. Now, we've seen something like this before when we were talking about the energy states of like a quantum harmonic oscillator or of the infinite square well. When we found the expectation value of the energy, it had exactly this form. It was the sum over n of Cn squared times En. And that's because those stationary states that we were using are eigenfunctions of the Hamiltonian. And we just didn't use that language. And so what we're seeing here is that if we can find eigenstates of some operator, then the expectation value of that quantity is going to be given by the same sort of sum that we used for the energy states of the harmonic oscillator and the infinite square well. So for the eigenstates of operator Q hat, the expectation value of Q is going to be the sum of Cn squared times the Qn. So this is just like the expectation value of E for stationary states. And like I said, that's just because the stationary states are eigenfunctions of the operator H hat. So if I was to replace this with H, the expectation value of the Hamiltonian or the energy, it's just going to be En times Cn squared and sum over n. Okay. So let's see if we could work this out for something that is not a discrete set of states, but something that's continuous, like the momentum. So what is the probability that a measurement of the momentum yields a result in the range dp? Okay, set properly in the range p to P plus dP. So before we start this, I want you to just think about if I would have said, what is the probability that our measurement finds a particle at a position between x and x plus dx, then what we would say is we would take the wave function psi of x, we'd square it, absolute square, and we'd multiply it by dx, right? That's how we've been doing it. So what we're going to find is something kind of analogous to for this question about the momentum. So the answer is this coefficient Cp squared dP. And so we have to go about trying to find that coefficient. So we have to find this Cp coefficient. So remember what the Cp does is if I wanted to write some state in terms of the eigenfunctions of the momentum operator, I would have all those eigenfunctions listed out and they would be weighted by some coefficient. It's going to be a continuous function rather than a discrete sum over values of integer n, but it's still just a continuous sum or an integral. And that projection is we take our state and we take the inner product with the momentum eigenstates. Okay, and so the reason that I wrote down the momentum eigenstates at the beginning is because we want to use it right here. Okay, so this is what we found last time. So let's see what happens if we try to do this calculation. All right, so we'll have a factor of 1 over square root 2 pi h bar. The inner product involves an integral. That integral is going to be over x in this example. This wave function, we'll just write it down. And then we just need the rest of this eigenfunction. And so it's this exponential, but notice that this is the conjugate. So we're going to have to put in a minus I here. So we get e to the minus I px over h bar. And if you look at this, this looks just like the Fourier transform. So we have a function of x, and then we have some exponential involving momentum in x. And if we integrate over x, we end up with some function of p. So that's the inverse Fourier transform where we go from a function of x and end up with a function of p. Okay, so let's just make a note of that. Note that this is a Fourier transform. Fourier transform from position space phi of xt to momentum space Cp. Okay, in fact, usually what people do at this point is they define the C of P to be a wave function expressed in terms of momentum. And so then we can go back and forth between wave functions expressed as a function of position and a wave function expressed as a function of momentum. So this quantity is called the momentum space wave function. And it's usually denoted as phi of pt. And so therefore, what we have is phi of pt is equal to 1 over square root 2 pi h bar integral from minus infinity to infinity e to the minus px over h bar psi of xt dx. And we can go the other way. If I had my phi of pt and I wanted to figure out my psi of xt, I would do the inverse of this transform. So likewise, psi of xt can be obtained from phi of pt via okay, so it looks similar, except what's going to be different is we're going to integrate with respect to momentum. There's going to be some functions of x and p in here, but once I evaluate the p integral, I'm going to be left with just a function of the position. And so what changes is the sign of the argument in the exponential, and we have to put in our function of p rather than a function of x. And so this is like the kind of pair of Fourier transform and inverse Fourier transform to move back and forth between these functions of momentum and position. So now we can say the following: the probability of finding a particle between x and x plus dx is, well, we've known that for a long time. It's the square of the wave function times dx. But now we have to be careful and just clarify that it's the square of the spatial wave function, the wave function expressed in terms of the position variable. But now what we're able to do is say the probability of finding a particle with momentum between p and p plus dp is, in the same way, we're going to take the square of the momentum space wave function and multiply it by dp. And so there's this nice symmetry between the two. Sometimes it's convenient to work in momentum space. We've seen when that's the case, when we have free particles, those free particle wave functions are very conveniently eigenfunctions of the momentum operator. And so it's nice to work in coordinates of momentum. All right, so one of the other big things that we're going to do in this chapter, which we're going to start right now, is we're going to do a derivation of the uncertainty principle. Up until this point, we've just said, well, we know that you've seen the uncertainty principle in physics 200. Sigma x times sigma p is greater than or equal to h bar over 2. So we're now in a position to see where that comes from. And so what we're going to try to do is to do a proof of the generalized uncertainty principle. And it's going to rely on some of the ideas that we've developed recently. So for any observable A. So we're going to imagine that I want to calculate the standard deviation of A. So we have all these replica systems, they're all prepared identical, and then we operate on each of these systems with our operator A hat, and we measure all the eigenvalues, we get some distribution, and I want to find the standard deviation. Well, the way you do it is you take your operator, you act on some state, you get an eigenvalue, and you take the difference between that and the average, and then you add them all up and average them. So it's like an average of averages. But before I do the second average, I square it. I square it so that these differences always come out to be some positive number, right? If I didn't square it, I'd get some positives, some negatives, they would cancel and they'd average to 0. And so what we're going to do is do this overall average. This is exactly what we did when we proved that the eigenstates have definite eigenfunctions, time independent. So let's see what happens here. So what we mean by this is we're going to take A hat minus its average value, whoops, or square it, and then we're going to find the expectation value of that. All right, so I've got this quantity in the center squared, so we can separate this out and we can say, well, I'll take one copy and act to the left, or sorry, to the right on psi. And then the other copy will act to the right on the other side. Okay. We're not going to do too much with this. I'm going to define this as some function f. So when I act with this operator, I'm going to get some eigenvalue and the eigenfunction back again. So it's just some number minus some number. And I just notice I don't have the square anymore because we separated the second copy over here. So I'm going to call this whole thing f, and then this is just the complex, the conjugate, the transposing conjugate of that same f. So all of this boils down to just some f inner product with itself. Okay. And so what we're going to do is we're going to say likewise. We're going to imagine that there's some quantity b that I want to evaluate the standard deviation for. And we do the exact same set of instructions. And we just define, I just write these as b's and then define that to be a g. All right. So to go further, what we're going to have to do is we're going to enforce the so-called Schwarz inequality. And what it does is it requires the following. If I take the product sigma a squared times sigma b squared, the way we've done it, sigma a squared is just the inner product of f with itself, and sigma b squared is the inner product of g with itself. And so the inequality is that this has to be greater than or equal to the absolute square of the inner product between f and g. Now, that's actually relatively easy to derive. Griffiths tells us how to do it. He has a problem in one of the appendices. And so the way you do it is you define gamma as g minus the inner product between f and g divided by the inner product of f with itself times f. Okay, so remember, these are just vectors. These inner products are just numbers. And so this is a vector minus some number times another vector. Okay, we can define that, that's fine. So then, if I take the transpose and complex conjugate of gamma, well, I'm going to get the transpose and conjugate of G minus. So let's see, it's going to be FG conjugate. This is just a number, so a number doesn't have a transpose, it just has a complex conjugate. But F inner product with itself is going to be a real number, right? Because it's going to be F conjugate times F, which is just the absolute square of F. So that's real. So it's just F inner product with F. And then we have F transpose and conjugate. All right. And so what we're going to do is we're going to evaluate the inner product of gamma itself. Now, before we actually go do the calculation, let's just recognize that, remember when we were talking about inner product, we said it was sort of like the analogous to a dot product where it finds the magnitude of some vector. So this is the magnitude of some vector gamma that we defined above. But the magnitude or length of a vector has to be a positive number. So this is greater than or equal to 0. So that's where our inequality is going to come from. Okay, and so if we do this, we're going to get G inner product with G is one of our terms. And then we're going to get plus, let's see, let's do this one and this one together. So we're going to get, I think, FG squared. And then in the denominator, we have F with F, but then we're going to get F with F. So that's going to cancel. Okay. So then what else are we going to have? Oh, sorry, I have to be careful. I have to be careful. When we do this and this together, we get F inner product with F squared in the denominator. And then we have F inner product with F in the numerator. So we cancel one factor. So I was wrong. We are left with one F inner product with F in the denominator. All right. And so now we have the cross terms. Okay. So we're going to get minus. So let's do G with this thing. So I'm going to get F G star F F, and then we're going to get F G. Okay, and then we're going to get minus, what's the other one? It's going to be F G, sorry, it's the wrong one. Now we're going to do this with that. So it's going to be FG and then we're going to get GF and it's going to be over FF. All right. Okay. Well, if we look at this times this, that's going to be inner product of F and G absolute squared. So these two are going to cancel. All right, so that's nice. So this cancel this. And then I think we're left with minus FG. But if I invert this one, it's the conjugate of this. And so it's FG squared. And then it's divided by FF. And that's it. And then plus G inner product with itself. All right. So we're almost where we want to be. So I'm going to multiply by f and its inner product with itself. So we could say that, let's see. So f, g, minus f, g squared. So I've just multiplied by f inner product with f. And then that has to be greater than 0. And so something greater than 0 multiplied by something positive is still a result that's greater than 0. And so this has to be greater than or equal to 0. And so finally, we get the Schwarz inequality, which we want to use. This has to be greater than or equal to inner product with f and g, absolute squared. All right, so this is what we're going to use. This is the so-called Schwarz inequality. And that's the end of our little aside. Okay, so let's just remember where we were. We were going to say that this product of these two standard deviations squared had to be bigger than this quantity. And so I want to focus on this quantity now. It's just going to be some complex number. Any complex number I could write as a real component plus an imaginary component. So we say next, for any complex number, z could be written as x plus j times y. We require the following. Z squared, absolute squared, is going to be x squared plus y squared. And clearly, that has to be bigger than y squared. We're going to introduce a second equality, right? X squared is some positive number, y squared is some positive number. So two positive numbers have to be bigger than one of the positive numbers on its own. All right. But we can write y squared in kind of an interesting way. Let's imagine I took z and added to it its conjugate. So that would be x plus jy plus x minus jy. And the jy's would cancel. That would just be equal to 2x. What if I did something different? What if I took z minus its conjugate? I'd get x plus jy minus x plus jy. It's going to be 2jy. And so I can, I guess, sorry, we're using usually I'm getting confused with electronics. So we'll use I. So z minus z star is going to be 2I times y. So that means I could write y as 1 over 2I, z minus z star. And then for us, I need to square it. Okay. So therefore, if we write this inner product with just some number, could be a complex number. If we say that that's equal to z, then we require that this has to be greater than or equal to, well, this y squared is like this. So it's 1 over 2I. And then it's the difference between our complex number, which is f inner product with g, minus the conjugate of z, but the conjugate of z is just g inner product with f. So z conjugate would be g inner product with f. So I'll write that g inner product with f. And then we have to square it. Okay. So what we're going to do is we're going to combine the two inequalities, one at the top of the screen and one at the bottom of the screen. F inner product with f times g inner product with g, that's our sigma a squared times sigma b squared. We're going to say that has to be greater than or equal to this quantity here. And that's going to lead us to our uncertainty principle. Okay. So combining the two inequalities, we have, okay, so this is what we started with, and this has to be greater than or equal to now 1 over 2i fg minus gf squared. So we're getting close to what we want. Does this remind you of anything like a fg minus gf? What does that remind you of? Usually, if we do like a AB minus BA, that just evaluates to 0. Yeah, it's the commutator. So we're going to get like a little commutator that's going to pop out of this. Okay, so now FG. Well, remember the way we defined F. If we go all the way back here, where did we define F? Here it is. It's written in terms of these A hats and the expectation value of A. So let's just put that in. So for F, we had an A hat minus the expectation value of A. And then that's acting on our state. And then the G is the same thing, but it's written in terms of the B hat operator and the B expectation value. Okay. So now we'll kind of do the reverse of what we did before. I'm going to flip this thing around and we'll have A hat minus expectation value of A times B hat minus the expectation value of B, like so. All right. And so now what I want to do is I want to just expand this product. I'm going to just multiply this out. We'll get 4 terms. Okay, what's the first one? It's A hat, B hat. Okay, and then we have minus A, B hat. Expectation value of A, just some number, times operator B hat. And then we have, let's see, minus A hat B. So I'll go minus expectation value of B, A hat. And then what do we have? Minus and minus is a plus, so expectation value of A times expectation value of B with a plus. And I need to move this over. Okay. So let's see. This is equal to A hat, B hat. All right, but if I just think of A hat times B hat as some new operator, C hat, then psi C hat times psi is just the expectation value of that operator. So this is the expectation value of A hat, B hat. All right, and then we have minus A is just a number. So when we evaluate this inner product or expectation value, it's an integral. A is a constant, it comes outside the integral. So then we have psi b hat psi. But this is just the expectation value of b. All right. Then we have, let's see, minus b psi a hat psi. This is the expectation value of a. And then we have plus a expectation value, b expectation value. All right. So you could see actually 3 of these terms are the same, maybe except for the sign out front. So 2 of them are going to cancel. So I could cancel these 2, and we're just left with the first 2 then. So this cancels with that. Okay. So therefore, what we were working on was the inner product of F with G. And so we've come to the conclusion that that's A hat B hat minus the expectation value of A times the expectation value of B. All right, now if we go back and think about what we're trying to do, is we want to put that into here. So we also need G and F in the opposite order. If you actually work that out, you would find that it's just the order of the operators in the first expectation value reverse. And so it's not necessarily the case that A hat and B hat is the same thing as B hat followed by A hat. It's because, you know, one of them could involve a derivative with respect to X, like the momentum operator, and the other one could have an X in it, like the position operator. So whether you do the derivative first or second matters. Okay, and then it would still have the expectation value of A times the expectation value of B part. All right. So when we actually go and look at the difference between the two, the second term is just going to cancel, and we're going to be left with expectation value of A hat B hat minus the expectation value of B hat A hat, which we could write as following. But as we already guessed, this is just the commutator between the operators A hat and B hat. And so therefore, this kind of abstract quantity that we've been working on boils down to the expectation value of the commutator of operators A hat and B hat. So it's kind of a pretty result, actually. So what we're going to do is we're going to go back and we're going to plug this in to this expression. Where is it? Here. So we just have to divide by a 2i. And remember, this is sigma a squared and this is sigma b squared. So the generalized uncertainty principle is sigma a squared times sigma b squared has to be greater than or equal to. So there's a 1 over 2i. And now what we've worked out is that fg minus gf is just the expectation value of the commutator of the operators A and B. So let's try it. Let's try it for what we know must work. If we make A, say, the position, and B, the momentum, we could check it. So let's suppose A hat is going to go to X hat, and B hat is going to go to P hat. We already know that the commutator between X hat and P hat is IH bar. Okay, so then the expectation value of X hat P hat is just equal to IH bar inner product of some normalized state with itself, which is just 1. So that's just IH bar. Okay, and then you can see what's going to happen. We plug that into here. The i's are going to cancel, and we'll end up with an H bar over 2. And so therefore, sigma x squared, sigma p squared has to be greater than or equal to H bar over 2 squared. Now we can take the square root and say that sigma p has to be greater than or equal to H bar over 2. And so now what we could do is we can check other pairs of operators if we want to. If they commute so that this A hat, B hat is 0, then the product of their standard deviations, sigma A and sigma B, has to be greater than or equal to 0. In other words, we could know each of them with infinite precision. If that commutator turns out to be non-zero, then it means that we cannot know both of those quantities simultaneously. So any pair of observables whose operators do not commute are called incompatible. Incompatible observables. So position and momentum are incompatible observables. So we can't know A hat, B hat simultaneously with arbitrary precision if this commutator is not equal to 0. All right. So we've got about 15 minutes left. And so what I want to do next is I want to go and think about section 3.6. This, what we just finished, this generalized uncertainty principle is section 3.5. So we're now moving on to vectors and operators. Okay. So we can use the inner product notation and our vector analogy to construct some useful operators and some identities that we'll make use of. So let's just recall, if I had some alpha z, beta z inner product, often you'll hear this called a bracket type notation. So what they've done is they dissected the word bracket into a bra. And this is like a row vector. And what they call a ket. So together they form the bracket or the bracket. And so this is like a column vector. And so when you multiply a row and a column, you end up with just a number. And so that's that inner product. So what this really means is we take alpha conjugate, which is some function of z, we multiply it with beta, another function of z, and we integrate with respect to z. Okay. So this is for a continuous basis. So what do I want to say? Let's say alpha and beta are vectors in our Hilbert space. So remember, that's the space of all square integrable functions. So it just guarantees that these inner products exist. Expressed in terms of a continuous variable, or let's say basis z. Okay, so the most common z would be either these are expressed as functions of position, like it could be phi of x and psi of x, or it's z is momentum, so that these are functions of momentum. So most commonly, z is going to go to either x or p. It's position or momentum. All right. If the basis is discrete, like the energy eigenstates of a harmonic oscillator, then we would have some alpha n, and beta n would be the sum of n alpha n star beta n. All right. So what I want to do is I want to start with the discrete case, and I want to define a new object that will be quite convenient for us. So starting with the discrete case, let's consider a new operator. I'm going to define an operator p hat. So this is capital P hat. This is not momentum. So this is going to be called our projection operator. So let me just emphasize, this is capital P. It's not momentum. Okay, the way we're going to define it is this weird object. So remember, if we're thinking of alpha as a row and this alpha as a column, now I have a column like, so it's n rows and one column. It's n by 1 multiplied by a row. And a row is going to have one row with n columns. So if I take an n by 1 object, multiply it by a 1 by n, I get an n by n object. So I would expect in a discrete case to get something that's like a square matrix. Okay, so p hat is called the projection operator. And I want to show you why. So, for example, let's consider p hat acting on some state beta. Well, just following our definition, p hat is this alpha object. This is sometimes called the outer product, just in case you ever come across that term. Okay, but the way we interpret these inner products, this is the projection of B onto alpha. It's like I took a vector in, say, a two-dimensional vector has an x component and a y component, and then I take a dot product with I hat. That's going to select just the x component. So this selects the component of beta that's aligned with alpha. Okay, so let's think about that. If beta was equal to alpha, then our p hat acting on beta would be the same as p hat acting on alpha, but that would just be alpha, alpha, alpha. If this is a normalized state, the inner product of alpha with itself is just 1. So 1. Alpha is perfectly aligned with itself. And so therefore, in this case, p hat acting on alpha is equal to 1 times alpha. And that's our eigenvalue equation. The eigenvalue is 1. All right. If, on the other hand, beta is orthogonal to alpha, then the inner product of alpha and beta would be 0. And that would mean p hat acting on beta is going to be alpha times this inner product, but that inner product is 0. Oh, sorry, no, it would be, here, let's write it out. So it's alpha, alpha, beta. Oh, so that's not going to work. Sorry, I got confused. So this is going to be 0. And so I guess we could write this as 0 times alpha, and so we get nothing. So there's no alignment of beta with alpha. Okay, so in order to see why this is useful, I want to do an example. And it's kind of an analogy. So let's do a Cartesian coordinate analogy. The idea is to try to frame some of this discussion with things that we're familiar with. So our basis vectors are, well, in Cartesian coordinates, we use basis vectors I hat, j hat, and k hat. And if we wanted to, we could think of them in terms of these column matrices. So I hat is just going to be aligned exactly along the x direction, j hat along y, and k hat along z. Okay, so if I was to try to construct the projection operator for the x-axis, I'm gonna do that with the I hat basis vector. And so it would look something like this. This is the column vector, exactly this thing, and then this is the row version of it. So this would correspond to 1, 0, 0, 1, 0, 0. And if we multiply this out, it would be 1 times 1 is our first element. And then we get 1 times 0 is our second element. And we'd get 1 times 0 again for that third element in that top row. And then you can see if I built the second row, it's going to be 0, 0, 0. If I built the third row, 0, 0, 0. Okay. So that's what the projection operator looks like for our kind of Cartesian coordinate analogy. Well, let's see how it works. Let's take this projection operator and act on just the I hat state. So we're asking how aligned is I hat with the X direction? And so we expect it to be perfectly aligned. And so it would be 1, 0, 0, 0, 0, 0, 0, 0, 0. And then we have a column, 1, 0, 0. And if you do this matrix multiplication, it's going to be 1 times 1 plus 0 times 0 plus 0 times 0. It's going to be 1. And then we're going to get 0 times 1 plus 0 times 0 plus 0 times 0. It's going to be 0 and 0. And that's just equal to I hat. So it's perfect alignment. And so this is analogous to what we said here, where if we said theta was equal to alpha, we get perfect alignment itself. And so that's the analogous statement. We could try the X projection operator acting on the J hat basis vector. Those are orthogonal, and so we're going to expect to get 0. So let's see. 1, 0, 0, 0, 0, 0, 0, 0, 0. And then we get 0, 1, 0. Okay, so 1 times 0 plus 0 times 1 plus 0 times 0 is 0. 0 times 0, 0 times 1, 0 times 0. We're going to get 0. And we'll get 0 again. And so this is like 0 times j hat, if we like. And so it's orthogonal. Okay, so that's nice, I guess. If we were to work out the projection operators for the y-axis and the z-axis, we would find for the y-axis, it would all be zeros except right in the middle. And for the z-axis, it would all be zeros except for right in the bottom right corner. So notice that similarly, if we did this for y, we would find this for our projection operator. And we did this for z, we would find this is the projection operator. What would I get if I added px, py, and pz? We'd get in diagonal matrix. What is that diagonal matrix? The identity. That's exactly what it is. So if I did this kind of sum, by this notation, what I mean is plus, whoops, that's backwards. Hello. J hat plus k hat. That's going to be exactly equal to, well, px plus py plus pz. And that's going to be 1, 0, 0, 0, 1, 0, 0, 0, 1. And this is the identity matrix. Okay, so next time, what we're going to do is we're going to identify this projection operator. If I sum over all of the basis states alpha, that's going to create for us an identity operator that we'll be able to use to try to conveniently express our states in terms of different bases. And so that's the direction that we're headed in. Okay, thank you very much. If you haven't already done so, your midterms and old assignments are at the front. And the submission for assignment 3 is also up here.